Hey everyone, I'm Ernest. I'm a software engineer at Microsoft, and I'm joined by Jiaxin. We're here to talk about a problem that many of us are starting to face. Our AI models are getting huge, but our GPUs aren't. In this talk, we're going to share how the industry is tackling this challenge with Kubernetes. Now, to make sure we're on the same page, we're going to structure this talk in two halves. The first 15 minutes or so will be less about Kubernetes, but more about giving the basic context on how to serve these large language models in general. We'll cover the fundamental concepts and challenges. The context is really important because it'll give you the foundations you need to understand the second half of the talk, where we'll deep dive into the Kubernetes strategies, architectures, and benchmarks. Now, before we deep dive, I want to give a special shout out to Professor Hao Zhang from UCSD. He generously allowed us to use some of his slides and diagrams from his previous talks, which do a fantastic job of illustrating some of the core concepts we're going to talk about today. OK, in this talk, we're going to start with the why, the motivations for taking on this challenge in the first place. Then we're going to break down the how into a four-step process. And after that, we're going to look at strategies based on model size, because a billion parameters model has very different needs than a 100 billion parameters model. And finally, part 4, we're going to get practical. We're going to show you architecture, special deployment strategy for Prefill Decode disaggregations, and a benchmark in Kubernetes to prove it works. We'll also cover the critical topics of fault tolerance. All right, let's start at the beginning. Why go through all this trouble? As we all know, GPU nodes are super expensive and requires a dedicated team of platform engineers to maintain. But self-hosting on Kubernetes gives you 3 main advantages. First, full control over data and privacy. When you use third-party API, your sensitive data leaves your environment. And by self-hosting, your data stays in-house, and you know it's not being used by someone else training. Second, model customization. You can fine-tune these models on your own proprietary data. You get to optimize the entire inference pipeline for your exact business needs, not just what the API providers decide to offer. And third, predictable costs. Those per token and per request charges from managed service can be unpredictable sometimes and adds up incredibly fast. So self-hosting moves you to a much more predictable cost model. OK, so we're convinced it's worth self-hosting models on Kubernetes. How do we actually do it? We see it as a 4-step process. First, model selections. You have to decide whether you need a reasoning model versus a non-reasoning model that generates fewer tokens. You also have to face the fundamental trade-offs of using a quantized model, which saves a little bit of GPU memory, versus a non-quantized model, which preserves the full accuracy of the model. Or maybe you want to deploy a foundation model with fine-tuned adapters. But it's really up to your business use case and how much you're willing to spend on GPUs. Second is model fitting, and this is the core problems of this talk. The model is getting bigger, so we use parallelism strategy to reduce the memory footprint on each GPUs. You can use tensor parallelism, pipeline parallelism, or expert parallelism. In this talk, we're using primarily TP and PP because expert parallelism itself is worth a separate talk. I recommend you guys to go check out the LLMD talks tomorrow, which will talk about YEP with VLLM and Kubernetes. Third is serving technique. Once you have decided your models and parallelism strategy, how do you efficiently serve these requests? In this talk, we're going to focus on Prefill Decode disaggregation, which is a very powerful technique. We'll also touch on emerging technology or techniques like attention FFN disaggregations. And fourth, holding it all together is GPU communications, both within a GPU node and across multiple GPU nodes. OK, let's double-click on step 2, model fitting, because this is where we hit our first 2 big problems. Problem 1, your model cannot fit in a single GPU. Say you have a model that requires 80 gigs of GPU memory to run, and you only have a GPU with 40 gigs of memory. It's not possible to fit the model inside that single GPU. And the solution here is to use tensor parallelism. Instead of using one GPU, you would have multiple GPUs in the same worker nodes. And with this parallelism strategy, you see it in the diagram on the left. we're sharding the model weights of each layer of the large language model across multiple GPUs within the node. This is also great for decreasing latency because we're essentially breaking down the forward paths into smaller ones and distributing to multiple GPUs, and then combine them together at the end. But it has very high communication overhead. Those GPU needs to constantly syncing with each other. So it really requires specialized hardware like NVLinks to connect all these GPUs together within the node. But what if the model is so big to the point where it can't even fit in a single node with multiple GPUs? That's problem 2. And the solution here is to use pipeline parallelism. And as the diagram on the right shows, we put the entire layers on different GPUs, which don't necessarily have to live in the same node. You can see that GPU 1 handles the first set of layers of the model, and GPU 0s from a different node handles a second set. This has very low communication overheads comparing to tensor parallelism, but it can lead to problems like pipeline bubbles, where GPUs are sitting idles waiting for previous pipeline stage, which means you might not be able to maximize your GPU utilizations. In the real world, we just don't simply pick one. We combine them together. And this is what leading frameworks like VLLM now recommends. The diagram shows the best practice hybrid approach. If you look at node 0, inside a node, we use tensor parallelism across all of its GPUs to run the first half of the model layers. Then we use pipeline parallelism to send the output across the network to node 1. Node 1 then used its own tensor parallelism group to process the second half of the layers. OK, so we figured how to fit the model using a combination of tensor and pipeline parallelism. That's a huge step. Now we have to talk about serving it efficiently. And this is where we have to reset our expectations. Because serving LLM inference is not like running a microservice on Kubernetes. A typical microservice handles one request, does one quick database lookup, and sends one response back. But LLM inference is completely different. It's a 2-phase long-running process with conflicting performance needs, or SLOs. For chat applications like ChatGPT, the most critical SLO is TTFT, or time to first tokens. This is what we called the prefill phase. It is very compute heavy because it has to calculate the KV cache. You can think of KV cache as something that caches the results of previous computations, and subsequent requests or token generations can reuse values inside the cache to speed up inference. But it grows linearly with your prompt length. So the longer your prompt is, the larger the cache gets, and the longer it takes for the GPU to compute that cache. And once the first token is out, we move to the decode phase. The decode phase needs that KV cache to generate the next tokens auto-regressively without reprocessing the entire prompt again. Here, we care about TPOT, or time per output tokens, which primarily bounds by memory bandwidth, not compute. And if we compare this with, say, a summarization task, the user doesn't really care about TTFT because they know that the TTFT is going to be a little bit slower than simply a chatbot answering your questions. All they care is the overall token throughput and getting the final results fast. So this diagram shows the prefill and decode phase in their simplest form. A single request arrives, and a single GPU worker processes it. And honestly, if we ever have one request in flight at a time, our job would be so easy. We wouldn't have any problems, and we probably don't need this talk. But in reality, that's never the case. We have to serve many users at once with requests for chatbots, code generations, and summarization tasks all arriving at random times. And this is where the real problem begins. When you try to put all these different overlapping requests on the same GPUs, you'll get interference. And to illustrate the interference, we need to introduce a concept called continuous badging first. Modern inference engines like VLLM use continuous badgings, which would batch prefilled and decode together from multiple concurrent requests into a single GPU cycle to increase token throughput and maintain maximum GPU utilizations. For example, on your left, there's request 1, or R1, which is in its decode phase, happily generating tokens for the users. Then R2 arrives. R2 needs a huge amount of compute for its prefill steps to process the initial prompt and calculate the KV cache. But it doesn't want to wait for R1 to finish decoding. So the scheduler decided to batch R1 decode and R2 prefilled in a single GPU cycle. Because they were sharing the GPUs, R1 decode get stalled, and this is what we call time wasted for decode. R1 time per output token just got terrible. And it's a lose-lose situation, especially when you have more and more concurrent requests. For example, on your right, we show that there are 3 new requests coming in while performing decode for R1. And as you can see, the decode phase from R1 to R3 are all interfered. And this is why sometimes when you're using LLM-based chatbots, you might notice a sudden lag when it's generating a response for you. And after a couple seconds, it will just resume back to a normal speed. So what's the solutions? It's simple but powerful. Let's just stop mixing prefill and decode in the same GPU worker. By scheduling them on separate GPU workers, we get no interference at all. The decode worker can perform decode without being interrupted, and when R2 arrives, it gets its own GPUs to do its prefill task and calculate the KV cache. And both requests can meet their SLOs. And this is the core idea of prefill decode disaggregations. And here's what it looks like architecturally. It's a simple logical flow. Instead of one monolithic GPU workers, we have 2 specialized pools. First, the prefill workers handles the initial compute-heavy KV cache calculations. And second, once the state is calculated, it is forwarded to the decode workers, which are optimized for fast, memory bandwidth-bound token generations. Now, it's definitely possible to run both prefill and decode workers on the same nodes with multiple GPUs using multiple GPUs. But as we discussed earlier, with model fitting, some of the largest models requires a significant numbers of GPUs just to run a single instance of the worker. And when they occupied all the available GPU memory in a single node, you have to deploy 2 separate pools across different nodes. OK, so this solves the interference problems, but it creates a new bottleneck. When your prompt is long, say you want to generate a summary of a 2-hour meeting transcript, the resulting KV cache is in the order of gigabytes. So now we have shifted the bottlenecks from competition interference to network bandwidth. How fast a prefill worker can physically forward that massive state to the decode worker, and this makes the physical connectivity of our Kubernetes worker nodes absolutely critical. And this brings us to GPU communications, our last step in our process. To understand it, let's examine the physical architecture of a Kubernetes worker nodes with 8 NVIDIA GPUs. First, at the bottom, we have NVLinks connectivity within the node. And these ultra-fast links is essential for GPU to GPU communications required within the same node. And second, we have cross-node communications. If we need GPU communications in a cross-node fashions, we need 2 things: the protocol and the physical high-speed link. For the protocol, we'll use RDMA, or remote direct memory access. This is key because it allows a GPU on one node to directly access GPU memory on another node by passing the CPU to drastically lower the communication latency. And second, the physical high-speed link. This is dedicated network fabric, typically InfiniBand or high-speed Ethernet. And each GPU is often bound to its own dedicated network interface card through PCIe within the same NUMA domain. So one busy GPU doesn't clog the entire node's network bandwidth. So now with this physical architecture, there's also another problem, the topology problems, right? A major challenge and buzzword you guys have heard throughout the week is topology-aware scheduling. And to simplify it, to explain it, when 2 or more pods sharing GPU within this same node with standard Kubernetes device plugins, the alignments between the claimed GPUs and the NICs is not guaranteed. And to give you a very concrete example, if one node claimed 1 GPUs and 1 NIC from this node with 8 GPUs, it can claim GPU 0 and NIC 7. And this forces communications to travel across NUMA nodes, which drastically increase the latency. And the solution here is also what the community is driving. Because standard device plugins failed here, the community is moving towards dynamic resource allocations, or DRA, which explicitly supports topology-aware scheduling. So I encourage you guys to go check out the KubeCon talks on DRA. Now, when should we invest in expensive ultra-high-speed fabrics like InfiniBand. It really depends on the workload. For pipeline parallelism, again, the communication overhead is so low that even normal Ethernet is sufficient. The traffic is very minimal. But for Prefill decode disaggregation across node, it's a non-negotiable, because transferring gigabytes of KV cache between nodes in millisecond timeframes requires massive sustained bandwidth and low latency. OK, so we have covered most of the steps. So let's put it together and see how these strategies change based on the size of your models. This table is a great cheat sheet. For tiny models, less than 1 billion parameters, we recommend using CPU or tiny GPUs for inference. You don't need any of this complexity. Obviously, you can still run large model with CPUs, but the token throughput is going to be so low that it's only suitable for running local experiments. For serving the most common large language models in production environments, let's say models with 2 billion to 100 billion parameters, you'll likely be on a single beefy node with multiple GPUs connected by NVLinks, for example. The main strategy here is going to be tensor parallelism to shard your models within the node. And you can also consider quantizing larger models to trade model accuracy for lower GPU memory footprint. And of course, if your applications is SLO sensitive, please use Prefill decode disaggregations, which we just discussed. And for the absolute monsters, 100 billion plus parameters model, you'll need it all. You'll need multiple nodes with fast interconnects. For dense models like Llama 405B, you'll need pipeline parallelism to shard layers across nodes. And for a mixture of experts models like DeepSeek or Kimi K2 thinking, you'll need expert parallelism and fast interconnects like InfiniBand. And now I'm going to pass to Jiaxin to talk about architecture, deployment strategy, and benchmarks.
Great. Firstly, yeah, let's talk about the multi-node deployment. The community now offers several approaches to multi-node orchestration. So today I'll focus on Airbricks Storm service, what it is and how it works. Storm service follows a 3-layer architecture. So the top level CRD encapsulates the entire LLM service. And the second middle layer, the role set is a cooperating set of roles. Think Prefill, Decode, or local cluster level router, or in multimodality like encoder or decoder, each with its own replica count, health gate, and upgrade order. So the leaf layer is the pod. So Airbricks provides 2 different PD deployment strategy. Replica mode treats each role set as an independent replica of the service. If you already know the PD ratio, like 3 prefill workers and 1 decode workers, you can directly configure the role set and replicate it. Routing will pick up the instance within the role set instead of picking PD workers from different role sets. In the poop mode, each role is supposed to be independently scalable. It is designed to handle scenario where different roles have different scaling needs. Router will pick up the least busy prefill workers and decode workers from the all instance under the service. So these figures demonstrate the substantial benefits of PD disaggregation in reducing inference time, latency, and increasing request load. Across both like 1P 1D and 2P 1D configurations, PD disaggregation consistently outperformed the non-PD baseline, maintaining low latency. So the performance gains are particularly pronounced at high loads. We observe up to 2x improvements in P95 tail latency for the 2P 1D setup, and over 5x improvements in median ITL in 1P 1D setup. So multi-node sometimes isn't cost effective. So in this benchmark, we compared the goodput we just talked about in earlier slide. We compared the goodput benchmark performance between full waste, quantized model with TCP, and quantized model plus RDMA PD setups. When we hold a very restrict goodput, meaning the target TTFT and TPOT are very critical for production standard, the quantized model plus the RDMA PD setup wins clearly. It delivers the 10x goodput with just half GPUs comparing to TP16 setups. So in total, over 20x higher efficiencies than the full width baseline. So the takeaway is when you move to multi-node, balance the cost efficiencies and the model accuracies. That's a super important thing to do. Fault tolerance is super hard under multi-node scenarios because the blast radius is super large. A single GPU failure can stall the entire deployment. To take the full-width DeepSeek R1 PD deployment as an example, if one single GPU fault can force a full instance, which means the 16 GPU restart, and 32 GPUs if you used like a Prefill and Decode coupled as the pod group or replica. So in MOE model with the EP and DP, so one fault can impact even higher GPUs, like from 32 to 96 GPUs. So the takeaway is if you choose multi-node, plan for the failure. You may want to ask, can we reduce the blast radius? I think the question is true. In VLM project, there's an ongoing proposal as the in-process fault tolerance to the inference engine, allowing to recover from certain failures without restarting the instance. So the goal is to minimize the service interruption and enable the rapid recovery. So on the control plane side, so Airbricks can aggregate the fault signals from multiple sources, mainly from the VLM engine level signals, and then apply the policy and choose the recovery actions and orchestrate it. So this is the joint efforts between the inference engine and the control plane on Kubernetes. Both work together to give a complete faster recovery solution. Let's talk about a new multi-node paradigm, attention and FFN. So those are two internal stages of the transformer forward pass. Attention decides which token to focus on, while the FFN is the per token MLP that transfers the hidden layer. Attention and FFN have very different compute and communication profiles. Disaggregating them let us specialize the hardware and scale each part independently. So think attention instance are memory access bound, and FFN are compute bound in decoding scenarios. So this is an emerging trend will likely become mainstream for multi-node serving in next year, just like PD disaggregation. But the solution is not free. To achieve optimal overall performance, so the processing latencies on both sides must be precisely matched. Any imbalance leads to pipeline stall or underutilized resources. So therefore, it is very essential to jointly orchestrate the performance and of attention and FFN and communication stages. So my suggestion is to treat the disaggregation or multi-node deployment as a design choice, not a default. So when the profile and network lines up, it wins big. Otherwise, it backfires.
Okay, let's quickly summarize everything we've covered. So first, we saw self-hosting is becoming essential on Kubernetes for data privacy, model customizations, and predictable costs. We broke the problem down into a 4-step process: model selections, fitting, serving, and communications. To fit these huge models, we have to use a hybrid approach of tensor parallelism and pipeline parallelism. To serve them efficiently, the key is Prefill decode disaggregations, which separates the initial processing of token generations to stop them from interfering with each other. Our benchmark proves that this PD disaggregation strategy, when deployed on Kubernetes with independent scaling, dramatically improves the tail latency under load. And finally, we saw that for these large multi-node systems, fault tolerant is a must. And by leveraging Kubernetes, we're moving from recovering the entire worker groups to a much more smarter pod level recovery. In the future, like attention FFN disaggregations will push our network even further, all in the pursuit of balancing cost and performance. And that's the end of our presentation. Thank you so much.
Okay. Oh, okay. This question is for Jiaxin. So, have you seen any difference of performance, like PD versus chunk prefill?
Yes. I think PD wins a lot if you need a very stable decoding performance, because once we separated the decode batch and prefill batch won't be mixed in single scheduling loop. So the decoding performance is guaranteed. That's why people prefer PD architectures in nowadays like model deployment, because the reasoning models take a lot of portion, and decoding length is much larger than previous ones. So decoding phase optimization is super important. So that's why I think people, I think in 2025, prefer PD as the preferred deployment strategy over chunk prefill. Yeah.
Hello?
What's the ratio? How do you decide what the ratio for P versus D pods or should be?
Yes, I think that's a good question. A lot of people, I think, struggle configure the right size, because if you cannot precisely configure the ratio, you waste the resources. I think the suggestion is to do the benchmark against your workloads, because different user scenarios, the prefill, the input length and output length are totally different. So technically, you can calculate how much prefill workers you need, and whether it's the memory bound or prefill bound by checking the TTFT and the TPOT. So once you have the profilers built for your own scenarios, and then I think choosing the right PD ratio is not that hard. So I think there's no golden rules for this question. The best approach is to test yourself, especially test against your workload traces. Yeah.
How does the data transfer for the attention FFN disaggregation compare to the data transfer for PD disaggregation?
Yeah, I can address that question. The attention between attention and FFN, the traffic volume is super large. I think we can probably talk about offline on the formula. The KV size can be calculated given the model and the data length. So that's everything can be quantized, measured. So PD, the transfer from P and D is not that critical. So that's why, like in our environments, we have different network topologies, and for PD is less critical than AFN deployments. I think based on your RDMA setups and even sometimes I know different cloud providers use EFA or some other fabric, so you can calculate whether the network part becomes the bottleneck. So I think that part can be calculated easily. Yeah.
Thank you.
I guess that's sort of my question. Like observability, what do you guys use to kind of observe what's going on, make sure that it's performing optimal?
Observability.
On perform or not perform?
Yeah, just observability of kind of what's going on in the environments for the different setups. Is it just you just have open telemetry hooks, or how do you guys?
So in the benchmark we showed above, we just observed the very standard inference metrics like TTFT, TPOT, and some of the GPU resource metrics, and also the network bandwidth metrics. So from the client side, because this is very easy to measure from the client side, whether the TTFT and the TPOT meet your SLO.
Oh, okay. So you're just looking at that as your okay. Thank you.
Yep.
So you talked about topology-aware scheduling within a node aligning NIC and GPU. Do you look at topology awareness between the nodes? specifically, like trying to put similar pods within the same rack or adjacent racks for lowest latency?
I can take. You
Yeah.
want to take that?
Go ahead.
Okay. Yeah, that's true. I think Ernest talked about the node inside like micro topology, and in production environments, especially for on-prem clusters, people build the GPUs well organized in rack S1 switch and S2 switch. So just as we talked, different deployment strategies have different network affinity requirements. Like AFN definitely have higher, and PD have lower, and non-PD doesn't have any. So based on your S1 and S2 switch network bandwidth, you can choose that. So I know a lot of Kubernetes schedulers already support the network aware scheduling mechanisms to help you achieve that. But in public cloud, I think this is super hard because a lot of cloud doesn't expose that many details to the end users. So there's probably only for example, a placement or HPC cluster to use. So I feel like that's a little bit hard to fine-grain control your affinities. Yeah.
So is this supported in the upstream kube scheduler, or do we need to use it?
Like a Volcano or Q. Yeah.
Yeah, to add on top of what Jiaxin mentioned, internode topology scheduling is actually a well-solved problem, in my opinion, because of the topology spread constraint API as part of your prospect. But for topology aware inside the same node, then I think it is getting solved by the community. Like there are a lot of ways to do it, but I think DRA is kind of going to be the standard, in my opinion, to, if you have multiple pods trying to claim or compete for GPUs and NICs in the same nodes, then you want to make sure that your GPUs and NIC that you claim is aligned to each other to minimize the latency. So yeah, there are two aspects, like internode and intranode, and I think internode is well solved, and intranode is like DRA. But, yeah.
Thank you.
Thanks.